On the 9th of October 2022, a pulse of light hit Earth. Not a gentle glow, not a shimmer on the horizon, not the kind of light you notice gradually, the way you notice sunrise. A pulse, instantaneous, extraordinary, carrying more energy than our sun will emit over its entire 10 billion year lifetime. It arrived at the speed of light, as all light does, having spent approximately 1.9 billion years crossing the universe. It originated in a galaxy nearly 2 billion light-years away, in an event so powerful that instruments designed to detect the most extreme phenomena in the cosmos were saturated, overwhelmed, reading off the scale. It lasted about 10 minutes. In those 10 minutes, it released more energy than the Milky Way produces in an entire year. Scientists called it the BOAT, the brightest of all time, a gamma-ray burst, the most powerful explosion ever recorded in the history of human astronomy, an event so extreme it rewrote the records, broke the instruments, prompted emergency observation requests from telescopes on every continent and in orbit, sent alerts through the global astronomical community in real time as the data came in. And the questions it raised about how it formed, what produced it, whether anything like it could ever happen close enough to threaten us, are questions that reach into the deepest, most violent corners of the universe. This is the story of the most powerful explosion in space. And it begins not with the explosion itself, it begins with what dies to create one. Not all stars die quietly. Our sun will not die quietly by human standards. In about 5 billion years, it will swell into a red giant, expanding to engulf Mercury and Venus and possibly Earth before eventually shedding its outer layers and leaving behind the cooling white dwarf, a long, slow, undramatic end by stellar standards. But some stars do not get that kind of ending. Some stars are born massive, 10, 20, 50, 100 times the mass of our sun. And for these stars, the giants, the supergiants, the hypergiant behemoths that burn so bright they exhaust their fuel in millions rather than billions of years, the ending is not a gentle exhale. It is a detonation. When a massive star exhausts the fuel in its core, the balance that has kept it stable for its entire lifetime, the outward pressure of fusion energy pressing against the inward pull of gravity, is suddenly gone. Gravity wins, instantly. The core collapses in less than a second. The outer layers of the star, still falling inward under gravity, collide with the suddenly rigid collapsed core and rebound outward in a shockwave of almost unimaginable violence. A supernova. The brightness of a supernova can, briefly, outshine an entire galaxy, a single star ending its life with a flash visible across billions of light-years. The energy released in a core collapse supernova is staggering, equivalent to the sun's entire energy output over roughly 10 billion years, released in seconds. But even a supernova is not the most powerful explosion the universe produces. For that, we need something more extreme. Some massive stars do not merely collapse into a neutron star when they die. Their cores are so heavy, so dense, so compressed by the infall of matter that not even the quantum mechanical pressure between neutrons can halt the collapse. The core does not stop. It collapses all the way into a black hole. And in certain configurations, when the dying star is rotating fast enough, when the magnetic fields are strong enough, when the geometry of the collapse is just right, something extraordinary emerges from that moment of black hole formation. Two jets. Beams of plasma and radiation fired simultaneously from both poles of the newly formed black hole at velocities approaching the speed of light, drilling through the collapsing stellar material, breaking through the surface of the dying star, and then blazing outward into space in the most focused, most energetic beams of radiation ever produced in the universe. These jets are gamma-ray bursts. And when one of those jets is pointing directly towards us, aimed at Earth by the random geometry of a dying star 2 billion light-years away, the result is what hit our instruments on the 9th of October, 2022. The boat. Its formal designation is GRB 221009A. The naming convention is simple: GRB for gamma ray burst, followed by the date of detection, 22 for 2022, 10 for October, 09 for the 9th, and A for the first burst detected that day. Simple nomenclature for an event that was anything but simple. GRB 221009A originated approximately 1.9 billion light-years from Earth, in the constellation Sagitta, from a galaxy whose central regions have not yet been fully resolved, partly because GRB 221009A itself is still so bright, even years after the event, that it outshines the galaxy around it. The burst was first detected by space telescopes monitoring the sky for gamma-ray events, the Fermi Gamma-Ray Space Telescope and the Neil Gehrels Swift Observatory. Within seconds of detection, automatic alerts were sent. Within minutes, observatories around the world were being pointed at the same coordinates. Within hours, the scientific community understood they were seeing something unprecedented. The initial gamma-ray pulse lasted approximately 10 minutes at its most intense. For comparison, most gamma-ray bursts last between a fraction of a second and a few minutes. This one endured. But the duration was not the most remarkable thing. It was the brightness. GRB 221009A was so bright in gamma rays that it saturated the detectors aboard the Fermi Gamma Ray Telescope, instruments specifically designed to measure the most extreme gamma-ray events in the universe, calibrated to handle brightness levels far beyond ordinary cosmic sources. They were not calibrated for this. Scientists had to reconstruct the true brightness of the initial pulse from indirect measurements and from data collected by other instruments that caught the event from different angles. The reconstructed energy output is staggering. In the first few minutes of the burst, GRB 221009A released energy equivalent to approximately 18 times the mass of the Sun converted entirely into radiation. 18 solar masses, in minutes, in one direction. The isotropic equivalent energy, what the burst's energy would be if it radiated in all directions equally rather than in focused jets, was calculated at approximately 10 to the 55th joules. The Sun's total lifetime energy output, 10 billion years of continuous nuclear fusion, is approximately 10 to the 44 joules. GRB 221009A released 10 billion times more energy than the Sun's entire lifetime output, in 10 minutes, from a single dying star. The boat was not just the brightest gamma-ray burst ever detected. It was so far beyond previous records that some scientists initially doubted the measurements. Statistical models of gamma-ray burst populations suggested an event this extreme should occur roughly once every 10,000 years. We happen to be watching. And the data it produced in the months and years of follow-up observations that have continued since is still being analyzed, still producing papers, still revealing new information about the physics of the most violent events in the universe. GRB 221009A did not just break records. It created opportunities. The afterglow of a gamma-ray burst, the fading emission in X-ray, optical, and radio wavelengths that follows the initial gamma-ray flash as the jet decelerates and interacts with surrounding material, is a scientific treasure trove. It carries information about the jet's composition, its speed, the density and composition of the material it is plowing through. GRB 221009A's afterglow was brighter and more detailed than any previously observed. The James Webb Space Telescope, Hubble, Chandra X-ray Observatory, and dozens of ground-based facilities all contributed observations in the months following the event. One of the most significant findings came from the analysis of the burst spectrum, the detailed breakdown of its light into wavelengths. Hidden in that spectrum were absorption features, the signatures of elements in the gas between us and the source, imprinted on the light as it traveled 1.9 billion light-years to reach our detectors. These absorption features are a map, a record of the chemical composition of the universe along that particular line of sight. GRB 221009A also produced a remarkable result in fundamental physics. High-energy physicists had long debated whether gamma-ray photons travel at exactly the speed of light, or whether extremely high-energy photons might travel at a slightly different speed than lower-energy ones. General relativity predicts all photons travel at the same speed regardless of energy. But some alternative theories of quantum gravity predict tiny, energy-dependent deviations. The photons from GRB 221009A were extraordinarily energetic, and they arrived at Earth simultaneously, within the precision of our instruments, regardless of their energy. No deviation detected. A confirmation of general relativity's prediction. A new, more stringent constraint on alternative theories. A dying star 1.9 billion light-years away, providing a precision test of the laws of physics. And the question of what specifically died to produce GRB 221009A remains under active debate. The most extreme gamma-ray bursts may require unusual progenitor systems, rapidly rotating, highly magnetized stellar cores collapsing directly to black holes, adding energy reservoirs beyond what ordinary core collapse provides. What is not debated is the outcome, the most energetic event in the history of human astronomical observation. A single star, a single death, one jet pointed at Earth, one moment of cosmic violence so extreme it saturated our best instruments and took months to fully reconstruct. The most powerful explosion in the universe is not a threat to us. GRB 221009A was 1.9 billion light-years away. At that distance, the energy reaching Earth was diluted across the vast distances of intergalactic space. It affected our ionosphere slightly. It posed no danger to life on the surface. A gamma-ray burst would need to occur within a few thousand light-years of Earth and be directed at us to pose a significant threat to the biosphere. Such events are extremely rare at those distances. But gamma-ray bursts are not irrelevant to us. They are intimately, foundationally connected to our existence. The most powerful explosions in the universe are the deaths of the most massive stars, and the deaths of massive stars, supernovae and the gamma-ray bursts they sometimes produce, are the primary mechanism by which the universe distributes heavy elements. The iron in your blood, the calcium in your bones, the oxygen in your lungs, the carbon that underlies every molecule of every living thing on Earth. All of it was forged in stellar interiors, in the nuclear furnaces of stars that lived, fused heavier and heavier elements in their cores, and then exploded, scattering those elements across the cosmos in the most violent events physics permits. Without supernovae, the universe would contain only hydrogen and helium, the two lightest elements. No carbon, no oxygen, no iron, no planets, no chemistry complex enough to give rise to life. Without the deaths of massive stars, we would not exist. The violence is not incidental to our existence. The violence is the reason for our existence. Every atom in your body that is heavier than hydrogen or helium was forged in a stellar explosion, was carried outward by a shock wave, drifted through interstellar space for millions of years, found its way into the cloud of gas and dust that collapsed to form our solar system, condensed into the Earth, was incorporated into the chemistry of life, passed through geological cycles and biological cycles and the long chain of evolution that eventually produced you. You are the endpoint of billions of years of stellar violence. You are made of the debris of dying stars. And the most powerful explosion ever recorded, GRB 221009A, 1.9 billion light-years away, releasing more energy than the Sun will produce in its lifetime in 10 minutes, is a modern example of the same process that built every atom in your body. Stars are born. They fuse hydrogen into helium, helium into carbon, carbon into oxygen and neon and silicon and iron. They live their lives, and then they die. And in dying, in the catastrophic collapse of their cores, in the rebounding shockwave, in the jets of radiation fired into the universe at nearly the speed of light, they give back everything they built. They give it to the gas clouds that will form the next generation of stars, the next generation of planets, the next generation of chemistry and biology, and eventually, in some improbable corner of some ordinary galaxy around some unremarkable star, the next generation of minds curious enough to point telescopes at a gamma-ray burst of a dying star and try to understand what they are seeing. The most powerful explosion in the universe is not an act of destruction. It is an act of creation. A star pouring everything it built back into the cosmos, violently, brilliantly, completely. And somewhere in the debris of that explosion, a billion years from now, in a galaxy we will never see, something may form that we would recognize. A planet, an ocean, a breath. Something alive in the remnants of something that died. The most powerful explosion in space is not the ending of a story. It is the beginning of the next one.